So listen, we will kick it off. Thank you so much, everyone, for joining us. I see the numbers starting to tick up as people enter the room. So, morning, everyone. Welcome to the afternoon of the first day of TMLS 2020. So far, it's been pretty interesting. I have the pleasure now of introducing David Duvenaud. I'm hoping I'm getting that correct. David's going to be talking about a cookbook for deep continuous learning. He works out of the University of Toronto as an assistant professor. And his research focuses on continuous time models, latent variable models, and deep learning. He did his postdoc at Harvard and his PhD at Cambridge. And he's also the founding member of the Vector Institute for AI, and also a co-founder of Invenia, an energy forecasting and trading company. I'm sure he'll correct me on that one as well. I'll just say, pretty impressive CV. He's done more in a couple of lines than I've done my whole life. He teaches more interesting classes than I've ever taken. Probabilistic learning and reasoning, statistical methods for machine learning, learning to search, learning discrete latent structures, differential inferences and generational models. He's got it pushing 50 publications. Frankly, I stopped counting at 30. And he's co-developed and autographed a pure Python automatic differentiation package. So pretty impressive brain we've got here today. I'm looking forward to what you've got to say. David, over to you, sir. Looking forward to learning, and I'm sure we'll have lots to hear from you. For everyone on the call, just put your questions in the chat, and we will try to get them at the end of the session. Thank you so much, David. Over to you.
Oh, my pleasure. And actually, while you mentioned it, Stuart, so I think this is a perfect audience. Speaking of courses, I'm going to be teaching a course on data science, a third year and fourth year course in January. And it's a project-based course. So if any of you have data that you would like a class of, third and fourth year undergrads in this data science program to spend a couple of weeks analyzing and fitting models to and, making little project presentations on, I would love to talk to you. And here, I'm just going to type my email in the chat.
David, I got that for you. You work on your session. I'll put your email in the chat for you.
Okay. All right. Anyway, I would love to hear from anyone who has data that they would like amateur analysis of, and to come guest lecture in the course. Okay, but today I'm going to try to tell you about some interesting developments in continuous time models. And I think this is like a good time to be talking to an industrial audience because there's some new tools that are just coming online that I'm pretty happy with. Of course, I toot my own horn here. So let's see. So, and just as a jargon warning, I want to say, I think as far as I understand, all of you have very different backgrounds, and especially those who come from like maybe an engineering background, probably already learned about some of the things I'm going to talk about, but just with different words. So please feel free to stop and ask questions, in the chat. I don't want anyone to just, say, well, it's not for me. The audience is always right. Okay, so the motivation for all the stuff I'm going to be talking about today is that whenever I've talked to people in industry or medicine or really anyone doing applications with machine learning, most of them say, oh yeah, okay, I believe deep learning is effective, or at least that I need to fit a large model if I want to make accurate predictions. But when I, show people my data, it looks like this, where I have, maybe this is time. And so this is actual data from one patient in an intensive care unit for 48 hours. And these little bars here represent all the different types of measurements that doctors and nurses were making of this person, like taking their blood pressure or their temperature or measuring their blood oxygen and stuff like that. And the point is they end up with this irregularly sampled time series data set. And it's not really clear, I think, how to fit that into any modern deep learning model. Like obviously we have very powerful time series models for like video and sound and text you could kind of say is a sort of time series. But they're mostly set up to handle data that comes at regular intervals. And so what people do is they go to great lengths to somehow shoehorn their data into regularly spaced data or regularly spaced bins. So they'll just average all the data over an hour or a day. And I think this is horrible, right? Like we are, at least from a modeling point of view, it's embarrassing that we built all these models that can't meet the data where it lives. And I think in the future, we're going to have some sort of Hippocratic oath for statisticians that says, thou shalt not mess with the data or average it or bin it or whatever before you send it to your model. So the first part of this talk is basically going to be, how do we handle this data without binning? I'm going to go through like the standard approaches, and then I'm going to go through the sort of fancier new approach that is very bleeding edge, just, so, but I think getting ready to be used. So the standard simplest options that I'm kind of going to dismiss a little bit are, one is continuous time Kalman filters. So Kalman filter just says that there's some hidden state and it has linear dynamics and you have Gaussian observations. So this is like what's used in like missile tracking, where they have like radar returns and they're trying to track the missile. So for very simple dynamics, it's a great, it's cheap, scalable, fast, but it's very limited. There's only a few parameters that you can fit in such a model. And if you try to have a huge latent space to get around that, then you have this cubic cost and everything goes up. So Gaussian processes, this is my bread and butter. This is my PhD, trying to fit Gaussian processes to interesting time series. And I guess I would say they're very nice theoretically. They don't overfit very much, but they are slow, although there's ways around that if you're willing to make it complicated. But fundamentally, they have limited expressivity. And I spent a lot of time trying to shoehorn different types of structure into Gaussian process kernels, but really having them do smoothing or learning some sort of like periodic dynamics. If you have a simple time series that has like weekly and daily dynamics, then that's probably okay. But if you're trying to model like customer behavior or something that you don't think, operates all that well periodically, or even like medical data, there's just, again, like sort of not enough parameters in there. All right. And so there is one really nice option that I think people have tried, which is recurrent neural networks, where you just feed in the data as it comes, even if it's irregularly spaced, you just feed it in order, and maybe also tell your neural network how much time elapsed since the last observation. This is a really simple and fast to get up and running. It's expressive, and in fact, like probably for a lot of applications, this is like where you should start and end, especially if you have lots of data for every customer. But the awkward part comes from when you have like a new patient or a new customer, not much data, then your neural network's not going to do a good job of characterizing the uncertainty about these new like people, basically. And I'd say that's usually when we have to make the most impactful decisions about what we're modeling. So the approaches that I'm going to talk about today are going to mainly focus on latent variable models, which are designed to handle low data or like very irregular data sampling settings. But there's a recent paper from 2012 from an old colleague of mine, Ben Marlin, that really, I would say, provides recipes for how to handle, or how to, like, all the different ways that you can build recurrent neural networks to handle irregularly sampled time series. And I'd say with a caveat that his models usually assume that the data is coming like very regularly and you have just like a lot of it. So that's a whole tutorial that I am not going to give today. The tools that I'm going to suggest that we use to handle continuous time irregularly sampled data are based around differential equations. And it might sound like, okay, we're going to go off into horrible math land and never come back. I guess I'll say, don't worry. At the end of this, we're just going to assume that we have a function called like ODE integrate, and that's going, or stochastic differential equation integrate. It's a black box that can just be a layer in our models, and it's actually pretty easy to hook up models that use these internally. Okay, so I think that probably a lot of people here even know more about differential equations than I do, but just so we're all on the same page notationally, Kaplan-Meier, we'll have to talk about that more later. So let's imagine we're going to assume that the system we're modeling, like the person or the business or whatever, has some vector valued state. Maybe it's like 100 dimensional, like 100 numbers that describe what's going on with them. And to learn dynamics in a continuous time setting means we need to specify a function that says, given the state of the person at the current time, how do we think that their state is going to change as we let time go forward? So, and now if we want to make predictions with such a model, it's called a initial value problem, where the idea is that we know the state of the system at some initial time. Of course, we don't actually know the state. We'll get to that later. But then if we also knew the dynamics, we could say, okay, well, that person's trajectory is going to follow, or that planet's trajectory, whatever, is going to follow these dynamics, which makes this nice curve, which is described by this integral. And of course, we can't actually compute this exactly. So there's all sorts of, like, the simplest ODE solver, just to try to demystify them, is to say, oh, okay, well, we could just take the current state and then take a little step in the direction of the dynamics. And so what that looks like is we say, oh, the dynamics are facing this way. Let's just take little steps following these arrows. This is a bad solver, but luckily we have 100 years of numerics that will tell us, that have provided us with these really great adaptive ODE solvers that sort of, depending on how complicated the function is, will either take small steps if they have to, or will take large steps if everything is like simple and predictable. Okay, so that's just so that we're on the same page notationally. So how can we use this tool to build, I would say, like native continuous time models? Any questions so far? Okay. So the simplest thing we can do is we can take, I was saying, a standard recurrent neural network is one where we have some hidden state, another vector that represents our belief about or the neural network's belief about what's happening. And every time we see a new data point, like X, the ith input, we take that and our old belief and we combine them through some neural network that we've learned to get our new belief. So here's just like a little toy example of, here's time, and these little different lines represent different dimensions of H, and saying, oh, every time I see a new data point, I update my belief, and then in between data, nothing happens. So that's one of the problems with the recurrent neural network setting, is that that's a little bit unrealistic. And if I haven't seen data or important data for a while, that's also something that's going to change my beliefs. So imagine that I'm like waiting for my friend at the bus stop, and I said, he said he was going to meet me at a certain time, and it's just I'm waiting and waiting. My belief about what's going on with him and when he's going to show up, and is he injured or who knows what, is going to be changing continuously through time as I wait, as I don't see new information. So we can just say that, oh, okay, let's take a recurrent neural network, and in between these observations, let's parameterize the dynamics of our belief state and let that also change through time. And now this is useful in case I want to make predictions in between data points about decisions about should I show this customer this ad? Should I go home and stop waiting for my friend? Yeah, it's a very simple refinement, but I think is a step in the right direction for making recurrent neural networks actually continuous time. And for the purposes of learning, we can just say, oh, this F is just some neural network. We don't really know much about it. We can make it be like a multi-layer perceptron. And just like we use gradients and stochastic gradient descent to train a recurrent neural network, we can train a model that has an ODE solve inside of it as well. That's something that's standard in all automatic differentiation packages these days. Okay, any questions about this? Is still the very simple part of the menu. Okay, so I kind of set up RNNs to knock them down a little bit. And I would say they're kind of weird for a few reasons. So one is, I talked before about how these systems have a hidden state, right? And for a system of planets, that's the position and velocity of all these planets, or the physiological state of a patient. But the hidden state of a recurrent neural network is not the same thing. It's and no matter how much we train, and no matter how much data we get, we don't really expect that the hidden state of a recurrent neural network will actually be the state of the system we're observing. It's kind of like if I'm watching a baseball game, you could scan my brain to learn about the baseball game, but the state is that what I'm thinking about is not going to correspond to what's actually happening. I also say it's not a well-defined generative model in the sense that we can't ask it to say what kind of data would we expect to see under this circumstance, or what kind of data would most decrease my uncertainty about this other aspect of the system. So I'm going to get into generative models later, but the beautiful thing about them is that you can basically ask them any question about the data that you can think of and answer that mechanically. Whereas a recurrent neural network can basically make predictions one step ahead, and that's sort of it. So for some systems, that's all we need. But in general, if we're trying to build a model that we're going to debug and use for all sorts of different decisions and live with, I'd say it's worth it often to make a generative latent variable model. And then this is kind of getting into the weeds a little bit, but the other thing is that we already know how to incorporate new evidence into a model exactly, or optimally, which is to use Bayes' rule. And recurrent neural networks kind of forget about that, and they just say, oh, I'm just going to have a neural network that sees information and learns how to process it from scratch. And that's really great when you don't have any idea of what your model should be. But it also means that you need more data to train things if you do have any sort of idea of what your model is supposed to look like. Oh, so question, what is the legend for the color lines in the graphs? This is like a toy problem where these are like maybe H is 3-dimensional. And so these are the 3 different dimensions of the belief vector. Normally H would be like 100 or 200 dimensional, but just to show you, I'm trying to show you what's changing as a function of time here. All right, thank you for the good question. Okay, so now I'm going to get into, this is the family of models that I think are totally underrated. And I'd say like they're a little bit harder to use than recurrent neural networks, so they shouldn't be the first thing that you try. But they sort of match reality in a really deep way. Okay, so there's a, since the 70s, people have been building latent variable models, such as the Kalman filter, that says that, okay, we think there's some true state of the world, this Z, that we don't get to observe. And these arrows are representing some function that says, how does the state transition at every time step? So this is like, given the missile's position and velocity, how does it change? And at every, this Z1 is like, the position and velocity at second 1, and then like again at second 2, at second 3. And then we only get to see these X's, which are like noisy observations that depend on the current state. So again, classically with Kalman filters, this is like the radar screen that you're looking at. And if we knew what the missile, where the missile was, we could guess what kind of radar screen we would expect to see. Yes. Okay, and so this is a probabilistic graphical model that these circles mean that there's also a little bit of randomness that happens. So even if we knew the exact position and velocity of the missile at 1 second, we wouldn't know exactly its position and velocity the next second. There'd be a little bit of noise. And same with the radar screen, there's going to be some noise. So this is really nice because we've written down a model we sort of believe that there's like the true state of the world that's evolving according to its own dynamics that we don't get to observe except for these noisy things. The problem is that if we want to compute, like usually the way we train neural networks is by maximum likelihood. And usually we talk about like minimizing the cross entropy loss or whatever, but that's equivalent, like almost every loss that we optimize is equivalent to maximizing the likelihood of the data given the parameters of our neural networks. To do that in these models, we have to somehow sum over every possible like state of all these Z's. So we have to imagine, okay, I saw these radar returns. What is the probability of every possible missile trajectory that I could have seen given those radar returns? This is like a very expensive integral to perform. It's an integral over like, if these ones are each 10-dimensional and there's like 100 time steps, it's like a 1,000-dimensional integral. And luckily in the last 5 or 6 years, we've worked out how to do these integrals approximately in a way where we learn to do them faster and faster. This is like variational inference or amortized variational inference or variational autoencoders. And I would love to give a whole tutorial on those, but the short answer is there's software that can do that for us now. And for example, this is a figure from the deep Kalman filter paper that says, oh, let's put little neural networks here in our transition dynamics and our emission probabilities and learn this whole thing from scratch. And they applied this to medical data, for instance. And there, lots of people have provided code to say, if you just give me time series that have these observations, I'll build a whole latent variable model for you automatically that then you can use to make all sorts of predictions, or even ask, like, you can even add actions to this model and say, oh, what if I give them insulin on this day? How would I expect it to change the trajectory? Okay, so, and yeah, this idea that we like learn how to do this integral quickly, we say we're gonna like build a recognition network that like learns to look at the data and guess what the trajectory was, but that's just kind of a detail to speed things up. Okay, so I'm sorry, like I don't have time to go deeper into latent variable models. I feel like it's a motif that's worth learning about, but we have to move on. But any questions at this point? Okay, so I was saying, this deep Kalman filter, I love it, and I think it's underused. And actually, Rahul Krishnan, we just hired him at U of T this year, so he's going to be starting next year as a professor, coming from MIT. So, work with him as well. So anyway, so one thing we could do is if we wanted to build a continuous time version of that model is to say, okay, well, instead of having discrete steps, which are always like 1 second apart, let's have an ODE let us make predictions about the state at any time. Right? Again, just solving an initial value problem like I showed a few slides ago. So the first model that we built to try to do this, to kind of bridge these gaps and bring these models to meet the data and continuous time settings, is to say, okay, let's imagine that there's some hidden state of the patient when he like enters the hospital or when he's born or who knows what, that we don't know. So circle means randomness, like we don't know what's going on there. However, if we did know it, we would be able to predict trajectory according to some dynamics function that we learn. And that's going to be like, this F function is like human physiology. It can be the same for every patient. And the idea is that every patient has the same laws of physics or physiology that they follow. They just happen to be starting from a different state. So this is how we're going to share data across patients. And then we can have any sort of likelihood model here, this P of X given Z. That's saying like, what is the probability that I would see a doctor's note with this recommendation or this temperature or this blood pressure given the state of the patient's physiology. So this is really flexible. This is something that we inherit from deep Kalman filters, is like the type of data that these latent variable models can handle is almost anything that like any neural network can handle, basically. So this could be, there could be like 100 different types of observations we can make. Some of them are like text, some of them are continuous, some of them are like discrete outcomes of tests, whatever we want. We can just condition on all of this and then jointly train everything in this model, the dynamics and the likelihoods and the posterior over people's states, all in one giant stochastic gradient descent optimization. Okay, so here's like a toy example of us doing that. So here is like one-dimensional data. This is just synthetic so that everything's low enough dimensional for us to see. But yeah, so here's like some data that has huge missing chunks. Here's like, imagine like 3 different trajectories. Like these are like 3 different patients and they're like ECG or something. And now this is us jointly fitting the dynamics function and the state of all the patients and the likelihood all at once in one joint optimization. So let's run it one more time. Yeah, and this is just the magic of stochastic gradient descent, which is that you might think there's a chicken and egg problem. Like, how do I know the dynamics until I know what the patients are doing? And how do I know what the patients are doing until I have the dynamics? It turns out it's fine. So yeah, you can see that we did recover, like these are samples from the posterior over the trajectories of these systems. This is a 2-dimensional slice of that F function that like says, given the current state, where is it going to move next? Here we made everything be 4-dimensional in the latent space, but we can make it be whatever dimension we want. The general rule is like, add more dimensions than you think you need, and the model will usually ignore the ones it doesn't need. Okay, so this is the simplest example we have so far in this talk of fitting a continuous time model to actually irregularly sampled data with stochastic gradient descent. Any questions about what's going on so far? Okay, so, and we actually did apply this to real data. Oh yes. So like I showed you this one example, that's like one patient from this Physionet data set that it has, I think, like a few hundred patients. And we tried a bunch of different simple models, like some of the ones that I told you about. So for instance, RNN delta T, that's the recurrent neural network, where it also gets to know what is the time since the last observation was made. So simple, fast, you should always start there. That's gonna be like your workhorse. And so like in terms of like making predictions or like, or even smoothing, interpolating, it does sort of okay. There's a bunch of different like ways that people allowed the hidden state to sort of like smoothly change between time steps before our paper, and they help. But then if you just have full ODE in between the observations that lets your belief state change, that does the best. And that makes sense because we're generalizing all these previous approaches. So it's like you can't not do better as long as you don't overfit. But I'm saying, that's again like a simple approach. It's like pretty good. Here we're trying a harder task where we're like extrapolating forward in time. And like this is sort of like the recurrent neural network baseline. what works better is one of these latent variable, one of these latent variable models, the one that I just showed you, this latent ODE. That's this model, and we think it's works better because it actually encodes this idea that we know that there is this true hidden state of the patient that's changing across time. There's one more refinement that we think there's an extra goodness that we can get from having continuous time models that didn't really help much in this setting. It made it a little bit better, and that is conditioning on the time of observations. So this is something that people don't usually do in latent variable models because they get an observation at every time. But the very fact that an observation was made can tell you a lot about the system that you're observing. So imagine if I had two sets of medical records where someone erased all the actual measurements. And so one of them is just someone who goes to the doctor once a year for a checkup. You think, well, regardless of what the doctor saw, probably they're pretty healthy. The other one is every year checkup, and then suddenly lots of different tests. Probably the second person has something going on with their health. And that's something you can guess pretty accurately just from looking at the timing of the observations. So we can actually also include the timing as an extra side piece of information, or even in principle learn just from the timing of information. And the reason people didn't really do this very much before was that, well, A, the RNN delta T does do this, but B, if you want to do this, you have to have this this integral of, okay, so what you have to do is specify some function lambda that says how likely am I to see an observation, how likely was the doctor to actually measure this given the state of the patient. Once you learn that, just to evaluate this probability, you have to solve another little integral. But our models already require us to solve a little one-dimensional time integral because we have to have an ODE solver to run the trajectories forward. So we can just add this in at not much extra cost. And the nice thing is that we can also now answer the question, when do I expect to see a new measurement, or when do I expect to see a new click or whatever from the user? So here, this is an example of one patient where after conditioning on all the rest of their data, we're showing, and their times, we're showing this is what the model thinks the probability of seeing an observation is at a particular time. And then the bars are happening when an observation is made. So it roughly does a pretty good job of expecting measurements to be made when they're made. Okay. Question: how do these ODE models compare to a dynamic Bayesian networks in which a generalization of the latent space models? Oh, dynamic Bayesian networks. Oh yeah, so these are not quite dynamic Bayesian networks. Actually, Stuart, this is unfortunate. There was a volunteer that just came in here, and I was asking her how long does the session run for, and she was saying 2:15.
Oh, okay. Well,
I mean,
just keep going then. That's great.
Well, so I'm not sure. So I'm happy to cut short or go to 2:15. I just want to make sure I don't mess up the schedule.
Okay. Why don't you keep answering questions? Let me just double check in the back end. So you keep going. Thank you.
Okay. Great. Yeah. So anyway, the last part of this talk is basically to say there's one last refinement that we can make, and the refinement is to add stochasticity to these continuous time models. So this latent ODE model, I'm saying that's a nice thing. You can download the code for it. I have well, it's easy to find the code. I think I have the code on later slides. But the weird thing is that it's deterministic, and it says, okay, given the initial state of the patient on day one, we, in principle, using this model, could exactly perfectly predict their health for the rest of their life. And obviously that's crazy. Obviously we think that there's all sorts of little random interactions happening that are not being captured by this model. And we want to allow for the fact that they took a drug or got hit by a car or whatever happens to them that we didn't model. Yeah, so it's we want to be careful about not misspecifying our model. So I was saying these common filters allow there to be randomness at every step in these transition dynamics. So what the last refinement is to say, okay, well, we also want to be able to say that we're going to somehow add noise whenever we take an infinitesimal step in our differential equations. And so what you end up having to model is, or you end up having to use stochastic differential equations, the standard thing from the last 50 years, where the idea is we keep the old ODE part of our model, this drift, that's the same. And we're just going to add another function that says how much randomness is there, depending on what the state is. Oh, okay, we're going 15 to 15. Great. So I didn't actually know anything about SDEs until like 2 years ago, but they have this kind of roundabout construction where there's this. So this sigma is a function that says how much noise should there be. This dVt is just a random Gaussian noise, and it's written as the like difference in time of Brownian motion just so that we can take limits appropriately. But you can basically say this is the deterministic part, this is the random part, and this is like scales the randomness. And just like Gaussian processes, this gives us a distribution over functions. Once I write down my drift function and my diffusion function, I've implicitly defined a whole, like depending on what noise I get, I'll get a different function every time. So this, I think, has all the elements we need for like this whole class of continuous time models. And the question is just like how to fit them to data. Okay. So any questions about like what I mean by like we're going to use SDEs or anything like that? Okay. Okay. So first of all, I want to say, when should we use SDEs? Because there's other ways to like we have like jumps or something in the model. And it's kind of cool. So the very first sort of stochastic differential equation that everyone learned about is called Brownian motion, and it comes from Brown, who's this biologist in like 18 something, looking at dead pollen particles and seeing that they still wiggled around and think like, well, are they still alive or what? And then Einstein, one of his first contributions to physics was to say, no, it's just they're wiggling because little water molecules are hitting them, and each one just makes a tiny little adjustment, and you just end up looking at this looks like wiggling. It's also a good model for like any situation where there's a lot of little tiny interactions that we don't get to see that are affecting the state, like allele frequencies in a gene pool. Every time two animals like have a baby or one of them dies, the allele frequency goes up or down a little, or every time two people trade or learn something, the prices in the market change a little bit. The cool thing is that I was saying, oh, this is Gaussian noise. You might say that's so limiting. That's like the Kalman filter. You said it was stupid because it's linear Gaussian. It's actually fine. The only reason we have Gaussian noise here is because the central limit theorem says that any sufficiently many tiny interactions will end up giving us Gaussian noise. So this is like a super, super general model class. So I'm, as a sort of deep learning person now, I'm going to say, let's just put neural networks in the dynamics and the drift and fit this to data, right? And I think, well, there's this like, why didn't people do this before, right? There's like a whole bunch of finance people who like sort of fit stochastic differential equations to data, but they only usually fit like 5 or 10 parameters. And the reason is that to ask for gradients of we have a scalar loss of some differential equation, we need to actually like store the entire trajectory that we were solving on the forward pass. We need to like somehow store this so that we can compute all the gradients we need if we want to do backprop or reverse mode automatic differentiation. So normally this is like too expensive, and like sometimes very big neural networks we run out of GPU memory. Same with like very big ODE systems, we run out of memory to compute their gradients. However, for ODEs we can just run them backwards to reconstruct the trajectory. So if we run this thing forwards, we get to this point, we can just build another ODE that has like negative dynamics and call another ODE solver and get this thing to be recovered to whatever precision we want. So we have like constant memory cost gradients. So it means we can train really large models. Surprisingly, when I started working on this a year and a half ago, no one had worked out a few little details of the math to run SDEs backwards in the way that we need to do the same thing. And like, you shouldn't take my word for it, right? That sounds ridiculous. And I was really confused about this for a while. But then actually in 2019, some serious probabilists wrote a paper saying like, we don't know how to run SDEs backwards, basically. That's like the missing piece. And that was really good timing because we had the missing piece, which is like the simplest thing. It's like, oh, well, okay, we have this extra function. Why don't we just stick some more negative signs in front of them? And then what we'll be able to do is like sample a Brownian motion, integrate forward, and then when we're computing gradients, just reconstruct things backwards by running another SDE with negative signs to reconstruct things. So I won't spend too much time on this, but astoundingly, this was like a mathematical detail that hadn't been worked out. Now we know how to run SDEs backwards. I'm going to kind of skip over this last part too. We also now know how to sample the noise in a way that like can be reconstructed without storing all the intermediate randomness by building this like virtual Brownian tree. So, like 60 years ago, this guy Pontryagin basically worked out how do you compute gradients for ODEs, and it's like you just call another ODE that runs backwards in time. And now in 2019, we have the same thing for stochastic differential equations. And it just looks like the same thing, but where you have an SDE solver and you have like the drift function running backwards in time. So this is like a new thing that means that we can do like have continuous time stochastic models that are scalable in all the ways that like deep learning is scalable. Okay, so that's what I just said. We still have to specify like a prior and a posterior on our functions. But that's I think I didn't leave enough time for this, but it's like you can just extend everything to the continuous time setting. It's like the same math for variational autoencoders. Okay, so the punchline is now we have a new class of models that we can scalably fit. Like obviously SDEs have been around forever, but I would say we didn't know how to scalably fit them with like millions of parameters and huge data sets until now. So here's a simple example of, we have some data. This is like, you know, just a one-dimensional toy example for visualization, but if the black crosses are data that's irregularly sampled, now these purple like trajectories, these are samples from the posterior. The blue shaded areas represent like the posterior density and saying, you know, here I'm very certain about where the function is, and over here I'm not very certain. And that's exactly what we want from a probabilistic model. And these gray lines, they're just representing sort of, this is the drift part of the stochastic differential equation in the posterior that's saying like, yeah, it's basically specifying what this distribution is on functions by saying like we need to steer towards the data. So fitting these models looks like learning this differential equation that sort of shows us how to like steer towards the data, but also back off and be uncertain when there's not much data, right? And it's sort of like automatically regularizing, and you know, the patients for which we have little data will be very uncertain, and later when you have more data, they'll be more certain, and then when we stop gathering data, we'll become uncertain again. But the difference here is that now we can have like millions of parameters in the dynamics that are shared across all the patients we see or customers or whatever. Okay, so I'm saying this is like a new model class. I need people to help me play with it. We've just started like applying this to like sort of real problems. Like here's us applying it to motion capture. You know, this is a sample from the approximate posterior of this like 50-dimensional data of motion capture. Here we're only fitting 11,000 parameters. This is like back when we had like version 1 of the software. It's much faster now. So now, you know, that's like tiny by neural network standards, but it's huge by stochastic differential equation standards. And everything we have scales linearly, just like normal neural networks. So we haven't like actually run this on any real data since then, but I'm pretty confident this, you know, we could learn 1 million parameters, no sweat. Okay, so the summary is we have these new, let's call it like stochastic gradient, there's stochastic differential equation based latent variable models that are now, I'll say like practical in the sense that like we have a proof of concept, and we think they can be made to work with a little bit of sweat and tears. That should let you handle irregularly sampled time series like natively with, you know, deep dynamics models and very flexible likelihoods. And then also this will let you answer all sorts of questions about like how certain you are about different customers or whatever. In practice, you should always just start with a simple recurrent neural network, because that's gonna like be the fastest thing. Code is available. And yeah, the next steps is basically, okay, make this a little more scalable, make it multiple timescales. But also I just want to talk to people who are doing like population genetics or finance or epidemiology or whatever, maybe they have traces of user behavior, to try to get some demos going, basically. Oh yeah, I'm trying to make this like multi-scale. I also want, for any programming language nerds out there, SDEs are like slightly not a great fit for GPUs because they have this like Brownian motion, these like tree data structures, these this like adaptive logic. So one thing I've been playing around with is like very niche, very bleeding edge programming language called Dex that's being developed at Google. Think like Julia, but if actual programming language academics who, you know, knew about fancy things like dependent types were we're in charge. Okay, so that's all I have to talk about today. I want to say the bulk of this work was mostly done by Zhoichen Li, who's an amazing undergrad who is going to Stanford now, and Leonard Wong actually did the hard proofs of this like reversible SDE stuff. And my students, Ricky and Yulia, did most of the experiments. So thank you very much. Any questions?
Thanks, David. I'm going to just let anyone know if there's any more questions from in. We've got a couple of minutes, but that was a great session, David. You managed to answer questions as we went, so not really sure why I was here. You both emceed and presented. Pretty impressive. All right, last chance for any final questions in the chat. Other than that, David, I'm going to say thank you so much. Great session. I have shared your email in the address, but to David's comment at the beginning, he is looking for collaborators and support. So either scroll up in the list or look for him on LinkedIn. David.
Yes, and for those who came in late, I'm looking for guest lecturers in my data science class if anyone has some data that they'd like my students to take a stab at in the spring term.
David, there's one last question. Are neural ODEs used in finance and show success? While you're answering that, I'll repost your email.
Yeah, so I would say neural ODEs, again, it's like a little bit hard for them to incorporate data on the fly. So as far as I've seen, there's a few flavors of neural SDEs that are starting to be used in finance. The thing is, yeah, with finance, like it's mostly secret, right? But people have sent me slideshows of like, there's slightly different ways to set up the neural SDEs to like in how they consume data that I haven't seen finance people using. But I mean, it's just like, I just see the math, the academic slides. I don't see like their performance numbers or anything.
Great. Thank you so much, David. We'll leave the call open for a couple minutes just so people can capture your email or any of the links in the email. But David, thank you so much. I really enjoyed it. I will see you around university. I occasionally show at University of Toronto. I'm down there lecturing myself. So maybe we'll run into each other. All the best. We'll see you through the rest of the day. Thank you, David.
Thank you. Yeah, and I'll stick around here for a little while.
Yeah.
Bye. And here's the code link if anyone wants it. Oh, thank you, Michelle. Oh, wonderful. Yeah, I'll check my LinkedIn. Oh, copy of the slides. Yeah, so there's, if you Google my name, yeah. So I have a copy of slides on my website, and I mean, I'm going to send these to the organizers, so I hope they make them available. But like a pretty similar presentation is already on my website with maybe just like different emphasis on the different parts. So, yes, thank you. Thank you, Stuart. Yeah, it does. It's nice to, there's a lot going on, but it's also nice because, you know, it's not all just replace everything with a deep net, right? That's always the first thing you should try. But like, I kind of feel like the last few years of machine learning engineering has been like very, I don't want to say like brainless, but it's just like, you know, this one trick over and over again. And now I think people are starting to say, well, let's, you know, we want to have some structure to our models, or like some algorithms are not, we shouldn't just replace everything with the neural network. So. Oh, so Jeremy, when were you doing EngSci? Oh, great. Thank you, Blair. Yeah, I wonder, is there a way we can get other people to like be able to talk? I feel like, you know. Okay. Yeah, that's around when I did my undergrad too. But I was at the University of Manitoba. I leave that off my bio. I should put it back on there. I actually got rejected from U of T when I applied as a grad student. I didn't have a very good CV back then. So. Yeah, and I think that link is to our paper, but it's a little bit focused on the mathematical details. So I'm hoping to have a more like application example, how to use these paper, well, whenever we get a nice collaboration going. Blair, is there a way that people can like also join in? We can make it more like a Zoom call. I feel like a Twitch streamer. This is great. Thank you, Jeremy. But I'm not like doing anything interesting like playing a video game. Here. Well, okay, if anyone's like still interested, let's see. What do I have in my... There's a nice meme that someone made right after the neural ODEs paper came out. There was a whole bunch of other papers that were sort of like saying, let's make neural stochastic differential equations. And actually, these people even changed their name of their paper after because they didn't actually like make them scalable, which I was happy with. But yeah, someone did neural ODEs. Well, obviously we should do neural SDEs. Anyway, yeah. So like in this kind of public talk, I don't really like to spend too long on all the related work. Like in an academic setting, I would spend a lot of time on this, but it's like basically, if you want to look at the related work, there's a lot of good stuff, but mostly they start by just discretizing time at the very beginning, but just very finely. So they're like, okay, we'll have every, 100th of a second we'll update, and that's sort of fine, but then it's slow if you make the discretization too fine, and it's bad model if you make it too coarse. So luckily we don't have to choose. We can let the adaptive solver figure it out later. Yeah. Anyway, yeah, and I mean, I guess like if anyone's like thinking about using this, the main limitation is that this is still like fairly slow compared to like the binning. Binning is just going to be really fast, right? Because you're only going to update once like every bin, but this is going to update every single observation you have. So, I don't think it's crazily slow though. So, yeah. Anyway, that's the presentation. I think I'm going to get going now. Thanks, everybody.